please.
Okay, thank you. So it's my pleasure to introduce today's speaker, Daniel Smania from University of São Paulo. He's going to speak about transfer operators, atomic decomposition, and base of space. Thanks, Daniel, please.
So thank you very much for the invitation, and thank you, Jacqueline, for the introduction. So I'm going to, that's my first webinar, as I told you, and if I do something stupid, let me know. If you're not listening, if the internet's too bad, I don't know. So let's see, okay? So, okay, why this doesn't work? Yeah. Sorry, I think I need to authorize something for. It's supposed to work. Are you seeing my?
Yes, yes, it's.
Everything. Okay, perfect. So let's see. Okay, everybody's seeing this, right? Okay.
Right.
Okay, so I'm going to talk about atomic decomposition, base of space in transfer operators. This is a joint work with Alexandra Biet, that's in the audience. So there are two preprints about this. You can find in the archive, transfer operators in atomic decomposition and transfer operators atomic decompositions in the bestiary. This is like a lot of examples of application of the theory that we developed in the first paper. Okay, so what I'm going to talk about, I want to talk about expanding maps. Expanding maps. Okay, so that's the introduction. So let's start with a very simple dynamical system, some expanding Markovian map on the circle, right? A C2 expanding Markovian map like this. So you know this maps has a unique absolute continuous invariant probability, and this is that is absolute continuous with respect to the Lebesgue measure. So that's the physical measure, the unique physical measure of this system. Okay, and we know, if you saw, if you did a course in ergodic theory, probably saw this example with details, and turns out that this dynamical system has a lot of nice properties. You have exponential decay of correlations for Holder observables. You have uniqueness of invariant probability that's absolute continuous with respect to the Lebesgue measure. There's only one invariant probability that's absolute continuous with respect to the Lebesgue measure. The observables that are, say, Holders satisfy central limit theorem. They also have very nice results when you perturb the map. So these maps are structurally stable. So when you perturb the map, you take like a smooth family of these dynamical systems. The measure, the invariant measure moves in a smooth way with the parameter. So this is called linear response. And I have a formula for that. This is a well result. And you also have something called analysis of topological pressure. I'm not going to define topological pressure, but this is very important in a lot of settings. For instance, if you wanted to understand how the dimension of dynamic defined sets changes when you change the dynamical system, right? So you have for instance, a contour set that is defined by your expanding map, is defined dynamically by your expanding map. You wanted to know how the Hausdorff dimension of this contour set changes when you change the function, right? So you actually have a differentiability of the Hausdorff dimension. So this is a road result by Bowen, and you can to do that you need this property, the analysis of the topological pressure. Okay, so what is nice about this is that there are many ways to prove these things. For instance, exponential decay correlations or uniqueness of the invariant probability. That is one method that I particularly like, that is using the study of the Huel-Perron-Frobenius operator, and a lot of people like this. So there is this linear operator in Banach space, defining a Banach space of functions like the Holder space of Holder functions. And if you study the spectral properties and other properties of this operator, you are able to prove all this stuff. Okay, this is not the only thing that you need, but it's the main thing. If you study the spectral properties of this, This is one of the most difficult steps. And if you understand this, the spectrum of this operator, then you can use another tools to conclude all this nice stuff that you see here, okay? And what is this property? Okay, so let me just introduce the Perron-Fermat. You probably know what is the Perron-Fermat operator, but in this case of expanding maps, it's very easy to define. The Perron-Fermat operator is a bounded operator in the space of integrable functions. M is the Lebesgue measure in this case, and you just apply, phi goes to L of phi, where L of phi is defined in this way. Okay, you make some kind of average around the pre-images of X of the derivative of the inverse of the branches. Okay, so that's the formula. And another way to write this is like this. For instance, in this map, you have two branches, phi 1 and inverse branches, phi 1 and phi 2. So that's the formula for the branches, right? I didn't put modules there because the derivative is positive everywhere in this particular case. Okay, but usually you have a modulus on here, modulus of derivative of phi here. Okay, good. And this is a very old tool. Actually, this was, as far as I know, the date of birth of this is 56 by a guy called Richard, who was studying the existence of invariant measures, nice invariant measures for many-to-one transformations. And there's this papers, like 12 pages, and he uses the Perron-Fermat operator as a tool to verify the existence of invariant measures that are absolute continuous with respect to some given measure. And in particular, I think he was the first person that wrote down this fact that fixed points of positive fixed points of the Perron-Fermat operator are invariant densities of your dynamical system, okay? But I think this paper is not very cited. It became famous because of this book of Ulan in '64, actually. There's a big book of problems in modern mathematics. There are problems in a lot of areas. And there is a short chapter about the Frobenius transform. He cites this transformation, the Perron-Frobenius transformation defined by Richard. And he asks if it's possible to prove for this operator the same kind of theorem that we prove for positive matrix, the famous Perron-Frobenius theorem for positive matrix. Can you prove something similar for this continuous Perron-Frobenius transformation, right? And he did some numerical stuff for the full unimodal map in the quadratic family, suggesting that that is the case. Okay, so this book, it seems that was usually popular in the 60s. A lot of people knew, of course, Euler and this book. And finally in 68, Ruel studied the Perron-Frobenius operator with a general potential. Now he replaces, it's not more in the interval, it's like in the space of symbolic space. We consider, instead of expanding map in the circle, you consider the shift operator, and you have some potential. This guy AGI is called potential, and you consider operator like this. And this, he actually proves something analogous to the Perron-Frobenius operator for positive matrix to this operator. Okay, and this has had a huge impact, especially after the construction of Markov partitions by. For general hyperbolic systems by, well, a lot of hyperbolic systems by Sinai. Okay, so you can transform, you pick like a Noz flow, a Noz diffeomorphism, pick a Markov partition, you translate everything to the setting, and boom, you can use this theory of Ruel. Okay, I think was pretty much at the same time, right? 68. Okay, so what kind of spectral properties you need to the transfer operator to be nice, to be able to prove this, all that stuff, right? So as I told you, the Perron-Frobenius operator in the interval, right, with the log of derivative has the potential, is always a bounded operator in L1, in the space of integrable functions. The problem is that the spectrum in this L1 is very big. Usually is the whole unit disk, the whole blue disk that you saw here, okay? Actually, the sensor spectrum is the same that the spectrum. So this is really bad. And this somehow reflects the fact that observables, integrable observables do not have nice statistical properties. You have some, okay, you have the ergodic theorem, but the final properties like the exponential decay correlations, central limit theorem, just doesn't hold for a generic guy in L1, okay? Okay, the nicer property would be, okay, analogy with Woolen, right? You wanted to see if there's some analogy with the finite dimensional case. Okay, in the finite dimensional case, operators has just, the spectrum is just a finite number of points, right? Isolated points. So one question that you could ask is, can you find a large Banach space? Let's say large, I mean like dense in a one, right? Cannot be finite dimension or something. So that this is a compact operator, the Banach operator is a compact operator in this space, right? So that would be the ideal situation because compact operators are very similar to finite dimensional operators. All the guys in the spectrum are eigenvalues except maybe 0, I think. And the accumulation points of the eigenvalues is always 0, right? So they never accumulate in the peripheral spectrum. They just accumulate at 0, right? Turns out that this happens sometimes if you pick some real analytic expanding map in the circle. But if it's just like C1 or C2 or C3, this is not going to work, right? It's very hard that you have compact operator. I know that a student of Viviane Baladi that are doing in some settings, you have this compactness, even it's not real analytic. I don't know the details, but Viviane can tell you about this. Okay, so this situation in the right is too good to be true. That situation in the left is too bad, right? It doesn't help you. So what we need is something in between. And this something between mixture these two properties. You have the following. Around the unit circle, in the periphery of the spectrum, is like a compact operator. And close to 1, you have this weird stuff. But close to 0, you have this weird stuff. But it doesn't matter because most of the properties that are described to you does not depend on what happens with the spectrum close to 0. It just depends what happens close to the unit disk, right? Of course, you can ask for finite properties, what people call it well resonances. And then you need to look closer and closer to 0. But that's not what we're doing here. Okay, so this situation, the weird stuff is much smaller. And if you can find a Banach space, large Banach space where you have this, like this mesh, is what we call it quasi-compact operator. Okay, I didn't give you the full definition, but it's like this. For instance, in this classical situation, C1 plus alpha expanding maps on the circle, you can pick the space of Holder functions. You pick the space of Holder functions and boom, you have this, exactly this image, okay? You can actually say something about the radius of this small ball here. It can be very precise in this case because it's a very nice dynamical system. Okay, so if you have the property in the middle, quasi-compactness, actually if you have something that a little more than that, is something called Lazotte-York inequality, we're able to prove a lot of things in that list that I show you. Okay. Okay,
Daniel,
so, yes.
Sorry, let me just add that Viviane wrote on the chat that it's more than C infinity is Gevry.
Ah, okay, yes, okay. But it's not real analytic, right? It's like, well, it's some class of functions that is not, yeah, right. Okay, Viviane told her. Okay, it's good to have a shot in the left. Perfect. Okay, so you have, okay, I need to skip this. I cannot go back, otherwise. Super. Okay, so what is the ongoing quest in measure theoretical theory of expanding maps? Is to find weaker assumptions on the expanding map. It's not so nice as that one that describes C2 expanding map on the circle. For instance, you can have this map is Markovian. You would ask for no Markovian. There are lots of results about this. You can have discontinuities. There are also lots of results about this. You can have irregular potentials. For instance, the derivative doesn't need to be holder. Could be like a piecewise holder, right? You could have zeros in the inverse of the derivative. The derivative of the inverse. Maps, potentials that are no holder does not have boundary variation. Another thing is irregular phase spaces, like fractals. And another thing that's bad is infinite many inverse branches. That's also something that's bad. So we would like to have these weaker assumptions and with bad behavior, but at the same time to find a wide class of observables where we'll keep having exponential calculations, central limit theorem, and everything. So this is a little different to, I know that people works like, you pick lots of people work, so you pick a parabolic point, so you're reaching the hyperbolicity assumption, right? You have critical points, and there are lots of very interesting stuff about this. But that's not what I'm doing here. I'm assuming uniformly hyperbolicity is really expanding, but you have weird stuff with this, right? Okay, so okay, this is the same thing. And what is nice is that you wanted to find a large class of observables. And a large class of observables, I mean, Sobolev spaces, for instance, with low regularity. There are results about this by Tomin, for instance. There's unbounded observables. There are lots of results about this. Sobolev space can be unbounded functions. So Sobolev functions can be unbounded functions. And what is nice is also to find natural classes of observables. So not ad hoc spaces, something like Sobolev spaces, Holder spaces, bounded variation spaces. These are all spaces that are lots of information in the literature with like natural classes of observables. Okay, so there's a lot of story about these. I'm not going to tell everything. So as I told you, once you get Markov partitions and Royal result, there are a lot of intense work to apply these in many settings. You have, of course, Royal, Sinai, Walters, Policott, Perry, a lot of other people that work with this Markovian setting. When you go outside the Markovian setting, you have many options. You can take inducent maps or towers, other things like this. But there are some people that work directly with the map, like for instance, this famous paper of Lazotto York. It considers piecewise C2 expanded maps. And then if you consider the space of boundary variation functions, you get the quasi-compactness. There is this generalization by Gora and Boyarsky for higher dimension. There's this famous result by Keller where actually he doesn't assume that the map is C1 plus alpha, is wrong here, but it's actually the potential the derivative has P bounded variation. There's also Suso for like using the same space that Keller used, but for multidimensional setting. There is this amazing result by Tsuji and Buzi about piecewise real analytic multimodal expanding maps. Okay, so there are lots of results about this. More recently, you have this result by Tomin, that's piecewise smooth maps on surfaces, expanding maps on surface. This is inspired by.
I'm sorry to interrupt. There is a question.
Yes.
Polina Vitnova is asking, what does p-bounded variation mean?
Okay. So this is a generalization of bounded variation. So bounded variation, you take the variation, you calculate the value of the function in some partition and take the differences in modulus, right? So in the p-bounded variation, you put the modulus, you put to the power 1 over p or something like this. It's a generalization of bounded variation, right? So every function that has bounded variation has p-bounded variation for p equals to 1. It's the same thing. And for p equals to 2, this is a weaker assumption about the function. Okay? And there are others examples like Livrani, Butterly, Islami. So Islami is not like functional approach. It's like using standard pairs. And you have a recent result by Nakano Sakamoto for expanded maps on manifolds using Bezoff spaces. In this case, you don't have discontinuities. It's a classical expanded maps on manifolds. Is very regular kind of dynamical system. Okay, so what are the main results that we wanted to talk about? The problem is that the main result is kind of very technical. So what I'm going to do is describe in loose sense the main result and then give you examples of applications that I think it would be more easy to understand, okay? So we're going to define a family of Banach spaces that in this family depends on 3 parameters, S and P and Q. And the phase space where you can define this space of functions has very mild structure. It's just a measure space with a sequence of grids. And what is nice about this is that this family of Banach spaces coincides with Bezoff spaces in many familiar settings, like the interval or a compact manifold or a shifted space. You can define Sobolev spaces in symbolic spaces, and this family coincides with Bezoff spaces in this and Sobolev spaces in this set. Okay, in this abstract setting, we're going to estimate the essential spectral ratios, that small blue ball that you saw in the picture, of transfer operators of piecewise expanding maps acting on this space. So the transfer operator is going to be continuous there, and you can estimate the essential spectral ratios. Can the phase space has fractal structure? Yes, could be like a hyperbolic Julia set, okay? A hyperbolic Julia set. Well, the symbolic space is kind of fractal, right? So you can have a conformal repeller and consider the invariant set. So all these are fractals. You can have a Rosy fractal and consider there. In all these settings, you can define these spaces. They're actually Sobolev spaces, and you can prove estimates for the essential spectral rates. Okay, so this is very nice. I'm going to give some examples. Good. I'm going to explain what's the grid soon. I'm listening. This is nice. So can you apply we can apply this for all the new expanding maps. I'm going to give the definition of the Banach space soon. Okay, and you can obtain statistical properties of observables in these spaces. Okay, so I'm not going to state the main results because it's a little too technical. It would take a lot of time to explain all the details. It's not difficult, but it's kind of technical, right? So what I'm going to do is to describe the bestiary. The bestiary is a lot of examples of expanding maps, piecewise expanding expanding maps, where you can apply this theory, okay? Some of them is going to be fractal, okay? Okay, so for instance, pick this one. This one is the most irregular kind of potential I can consider. So you take, but this particular example is a perturbative result. So you pick a piecewise affine expanding map in the interval, right? Like this, very simple, very regular. And then you perturb the branches. You add some GI. So this is the one of the branches. You make a perturbation of this for some GY. And this perturbation, the derivative is very regular. It's just a bounded function that belongs to this Bezoff space. This is a classical Bezoff space, okay? And the norm of this should be extremely small, very small. The L infinity norm and this Bezoff norm. Then the Perron-Frobenius operator of this new map is quasi-compact. To see how complicated can be this potential, this guy that I'm describing here belongs to this space. Okay, so we have infinite oscillations, infinite many oscillations going to some point. So this potential is not Holder, does not have bounded variation, does not have P bounded variation. So it's really, really complicated. Okay, so this is a perturbative result. What more can I have? So you can have like pick a piecewise expanding bi-Lipschitz map on the interval with 1 over p bounded variation, or bounded variation if you prefer. Okay, so you can prove Lazotte-York inequality in this Bezoff spaces. In this case, it's a classical Bezoff space. You can prove that every invariant density belongs to this. This is a consequence of Lazotte-York. And this is very nice. I don't think you can prove this in this setting before, that the invariant density, if you pick all the points where the invariant density is positive, this is an open set with a subset with 0 Lebesgue measure. Okay, so you can know something about, it's not exactly the support, but it's kind of the support of the density. Okay, and have a finite number of absolute continuous incorrect measures. And what is nice is that since you know this third claim that this set is open, topological things implies measured theoretical things. So topological transitivity implies ergodicity, topological mixing implies exponential decay correlations, right? And you can actually give a very nice upper bound for this essential spectral rates, very simple upper bound for the essential spectral rates in this case. Okay, but in this case, the map should be by Lipschitz, right? How about, let's say, other things? So you can get more regular maps, like continuous piecewise swan plus diffuse. In this case, you have a nice estimation for the better estimation for the essential spectral radius that you see here. And you don't need to put, so this is wrong, there should be P here. So you can pick P different of 1 in this case. What more? So you have Lorentz maps. So you can apply this for Lorentz maps in such a way, in the case where the singularities of the Lorentz maps are not flat. That means that close to the singularity, you behaves like x to the power L, or L is a number between 0 and 1. So in this case, you can apply this theory, and you have exactly the same things as before. So you don't need induction, you don't need the towers, nothing. It's just you straight apply the result for this Lorentz maps. The number of singularities doesn't matter, and so on and so forth. Okay. What's more? In the Markovian case, so you can define the Markovian maps, expanding maps in a very general situation, very abstract situation. This can be a fractal, for instance, if you ask. And in this case, you can have a very precise estimation for the essential spectral rates. More regularity of the map, Markovian expanding, implies that you have better estimations for the essential spectral rates. But in this case, there is a setback because the space is not a classical Bezoff space that you see in the literature. Okay. And this is the wing face map. So let's go to dimension 2 now. This is more complicated. So pick some square and subdivide in many, many, many little pieces like this, right? And each one of these square, you map to one of these rectangles that you see here. If these little squares are very, very small, you can prove all these results that you see here, okay? So for more than one dimension, we have these huge complications because the topology of the partition has some hole in into obtain this quasi-compactness and decay correlations, existence of invariant measure and things like that. So we should be more careful in higher dimensions. And okay, so this is weak face map. And you can have some genetic piecewise expanding maps. You have a result a la Coyleson. Sorry, I don't know if I pronounce it right. So you pick a partition of a domain D by domains with boundaries that is C1, piecewise C1. And you consider C1 plus beta expanding diffeomorphism in each one of the domains. For genetic maps in this class, I'm not being very precise here, sorry. For nice genetic maps in this class, you have all these results. In particular, this result about the invariant density, the support of the invariant density is an open set up to a subset of a 0 Lebesgue measure. So this, I think, is also new. I don't know, but I checked in the literature, I didn't find anything about this. Okay, And finally, you have a completely hyperbolic fractal setting. You can pick a hyperbolic rational map. And this map has some, Julia set has some Hausdorff dimension D, right? And you pick the Hausdorff dimension of this dimension and restrict to this Julia set. So this is all first regular metric space. And you can apply all the theory that you just described for this set. And you get quasi-compactness. So you can define a Sobolev space on the Julia set, not in the affiliating Julia set, on the Julia set. And you have exponential differential equations, central limit theorem, and all this stuff in this setting, this abstract setting. Good. So now I'm going to give you some idea of what kind of setting I'm working on and how you define this bonic space, okay? So how much time do I have? I speak usually too fast. And, okay. So the setting is the following. The setting is very easy. It's just a measure space with a sequence of grids. So you have a sequence of partitions, finite partitions like this. And this sequence has bounded geometry. Bounded geometry means the following. If you pick some element in the partition K, you pick a child of this partition, pick an element in the next partition that is inside the big one, then the measure of a Q and the measure of P are comparable. You can compare these two things. So that means that Q is not very small. It's also not very big because you have other childs here. So you can compare the two sizes like this. So I'm saying geometry, but it's as a geometry in a very weak sense. We don't know anything about the shape of these elements in these partitions or anything like this. It's just a sequence of partitions. So this is a grid. So I need just these two things, a measure and a grid. And these two things I can define this space. So that's an example of a grid. So you pick the dyadic decomposition of the interval 0, 1. Pick 0, 1 divided by 2, by 4, by 8, and so on and so forth. So we have a sequence of partitions, and this satisfies that assumption that I told you, bounded geometry. Another situation that's quite classical, you pick the square and make subdivisions in equal squares. Same thing. Another thing that's a little different, you pick a polygonal region and make subdivisions of a triangulation of this. Or pick a compact manifold and start with a smooth triangulation and make subdivisions of this in an appropriate way. So if you do that, it also satisfies this, all right? So there's a more abstract example. Pick a compact metric space with a doubling measure. So there is a result by Chris. It's not a complicated result. It's like 2-3 pages maybe, where he constructed very nice sequence of grids for this kind of spaces. So in this abstract setting, there is an abstract way to construct this sequence of grids with good bounded geometry, right? Okay. And finally, if you pick a Julia set with a hyperbolic rational map, you can also do that. You can also define the sequence of grids with a good geometry. Good. So that's a warning I wanted to do because I give this talk many times. And when you pick a sequence of partitions, because you work in dynamical systems, you usually think sequence of Markov partitions. But it's not the case here. Actually, when I work with interval maps, the sequence of partitions is going to be the dyadic partition of the interval, always. It doesn't need to have anything to do, the sequence of partitions doesn't have to do, is not related with the dynamics. But sometimes if your map is Markovian, you can pick a sequence of partitions has the grid, and then you get strong results because it's easier, right? So just to be careful about this. Okay. And this, just to finish it, let me just give an abstract set in the shift space. In the shift space, if you pick a Gibbs measure for a potential that is described here. So if you pick the sequence of cylinders of length K has the K partition, and pick this measure, you get a measure with a partition with bounded geometry. Okay, so that's a very general setting too, right? In this case, the sequence of partitions is the Markov partition of the shift, right? Good. So finally, I wanted to define the Banach space. And what's surprising is that I'm always tempted to define the Banach space in the beginning because it's very simple. And the idea to define the Banach space is very simple. You have these simple functions that are constant in the elements of the partition. So outside this element of the partition P is 0, and inside is constant. And the size, the height here is described by the measure of P. So this is the measure of P, elevate to the power S minus 1 over P. So this number is negative. This number is negative. My assumption is that these numbers are, this exponent, its power is negative. So what happens is that when you have, so because this number is negative, if P is very big, what you have is that the height is very, very small, right? So this is like a bar of soap, right? It's good to have around a bar of soap these days, right? You never know when, oh my God, a virus. But don't worry, you have a bar of soap. So what's going to happen is that, okay? So we have like this. And if P is small, what you have is the following. If P is small, the height of this atom is very big. This brick is very long, right? And this is like, could be like a vaccine, right? A vaccine, but this doesn't exist, a hand sanitizer, but it's always too good to have around a bottle of wine. So it's like a bottle of wine, right? Like this. So you have these bricks and you use these bricks, these blocks to construct your function. So this element is like a basis, but it's not a basis because there are many ways to construct the same thing. So what you do is the following. The green thing that you see here is the graph of the function, right? So this is the graph of the function. So you use these blocks, these atoms to construct the function. This analogy is not perfect because the blocks can be negative, can be complex, can be imaginary, and things like that. But that's the idea, right? And in this case, you can break bricks too. You can take fractions of bricks, right? And there are many shapes of bricks, right? That's given by that formula that I described before. That depends on S and P, right? So that's the definition, basically. So when you're building a wall, there are two questions that you do. How much is going to cost? So that's the point. If I give you a wall, a shape of a wall, there are many ways to build these walls with these bricks. There are many ways to do it. So of course, you wanted to minimize the cost of building this wall. So you wanted to use the minimal amount of bricks, for instance. You want to choose so less bricks as possible. And the second question is who is going to pay for the wall? But I'm not going to discuss this because it's not fashion anymore. And well, would be another kind of seminar. So let's discuss how much is going to cost to build this function using these bricks. And this is atomic decomposition. That's how you define the space. So this is your wall. Oops. So this is your wall, and you wanted to represent this as a combination of atoms. So AP is an atom where the support is P. So you can pick so much bricks as you wanted to. You can take fractions of the bricks. So CP is a number, it's a complex number. You pick a combination of these, and you represent this function this way. So that's a way to construct this wall. And how much is going to cost to define this wall, right? So the cost depends on these parameters, S, P, and Q. The cost is defined this way. For instance, if P and Q is exactly equal to 1, so this is just how many bricks you use it. Just how many bricks you use, how many fractions of bricks you use. So if this cost is finite, you say that this function belongs to this space, And actually, we call it this base of space associated to this measure in this sequence of grids, okay? So that's nice. There are many ways to define this construct.
Sorry.
Yes.
Daniel, I had a question.
Yes.
What is the role of S?
The role of S. Okay, so the role of S is related with how high are these functions, right? So let me show you. So S is in this formula, right? So the height here, this height depends on S, right?
Okay, okay, got
Right?
it.
So, so S is like the regularity of the function. You think it's like the Holder regularity of the function, right? But they're not Holder in general. Okay. So so P is like the integrability of the function. If you belong to this space, you belong to LP. S is like the regularity. So if you pick S very big in the Bezold space, the function is CS, right? This is very smooth. Bigger the S, smoother is the function, right? In the classical setting of Bezold space. Okay. Okay, so that's the definition. And you define the norm in this space has the minimal cost. So there are many ways to represent this function. And you can use, define this in many ways. I have just 10 minutes, okay, good. 15 minutes, right? So this is kind of very easy, right? So suppose I give you a function like this, and you want to represent this and to check if this belongs to these Bezold spaces. It's like to play Tetris. You put a block, a full block like this, then you divide by 2 and put 2 blocks with the base or half of this that you can fit this. So put a 1/4 block, 1/8 of the block, and so on and so forth. So we're going to fill up the form, the shape of the graph of the function like this. Okay, so that's nice because if you pick like a Holder function, for instance, you can check if the Holder function belongs to these spaces using exactly this method. So it's really easy, right? So let me go back to classical Bezold spaces. So these are spaces that we define in another paper that I didn't put the name. So it turns out that these spaces coincide with classical Bezold spaces in many settings. For instance, if you pick a cube and make these dyadic partitions, you get the classical Bezold space in this thing. If you pick a compact manifold with triangulations, you get the classical Bezold space, and so on and so forth. So you have many, in many settings, these spaces are natural spaces, and the spaces that appears in the literature before. Okay, I'm going to skip this. So there's a long story about atomic decomposition in Bezold spaces. I think I don't have time to talk about this. And finally, in the last 10 minutes, I wanted to explain to you why you have quasi-compactness of the operator in this setting. So the situation is similar to a tower, but it's not a tower. It's like an underground storage unit, right? So this is the level of the street, and you have a level. So this is the phase space. And you put, in opposite to towers, that you put copies of the phase space in many levels. You repeat these pieces of the phase space in many levels. Just in the part where you have some problem, here you put copies of the phase spaces in all levels, right? And there are markations in your underground warehouse. You see these marks here? So you're allowed to put mass just that respect these marks. So let me show you how you do that. You put blocks of mass functions. So this represents graphs of functions. And you can just put constant functions that are constant between 2 consecutive marks are 0 outside. So these are examples of functions that you can storage here, right? So it's like a Markovian tower, but it's a very Markovian, but even the shape of the functions is restricted, it should be constant there. And so this has nothing to do with the dynamics, right? Now I'm going to put the dynamics. I'm going to restrict some positions depending on your dynamics. So the dynamics has some branches. So you have this branch, this domain of the branch, this domain, and this domain. So what you do is the following. The blocks cannot cross between two domains. So this position is not allowed because this guy belongs to two domains. The same here, this guy. So this position here, so these lines are forbidden. You cannot cross these lines, right? And this is one dimensional, right? In this picture is one dimensional. So the intersection between two domains, they intersect just at a point. So these are real lines, right? More dimensions is more complicated, so something more complicated. So this position is not permitted. And this position is also not permitted. You cannot put things there, right? So you take off. So this is like a tower, and now you have a dynamics in this tower. So, but this is an underground warehouse now. Okay, good. So how you do that? So suppose you have a function. So this is an atom. It's the simplest kind of functions that appears in this guy. So this is a block, but the problem that this block respects the marks, but belongs to three domains, three branches. So what you do is that you start to cut the domains in pieces until each block belongs totally to just one branch. So you do this, and this, and this, and this, right? Now, every one of these blocks belongs to just one branch. So now you can storage the function. You can go to the tower, to the underground world. So you transport the mass to the appropriate levels like this.
Daniel, I'm sorry. The mass of the blocks doesn't, it's not related to the dynamics, no? It's just depending on the partition.
So it can be very high or very low. It doesn't matter. The only restriction is about the base, right? The domain. The domain should fit the marks.
Okay,
right?
Thank you.
And so you have like this, right? You just transport to the appropriate level. So this is like to go to from the phase space to the tower, but is similar, right? So this is called dynamic slicing. You adapt your representation in this space to a representation that fits the underground warehouse. So this is going to be important. So dynamic slicing in 2 dimensions can be extremely complicated because the domains now can be like this, could be smooth or have fractals. So here you have four domains of branches, and this square intersects all of them. So you need to decompose this square in infinite many squares, each one of them interior containing just one branch. So this dynamic slicing is extremely complicated. Okay. So how is the dynamics, right? So the dynamics is the following. Because this is like atomic decomposition, instead of pick an arbitrary function and see and apply the performance operator, I'm going to pick just an atom and apply it, right? It's like a basis. If you know what the linear operator does in the base, you can know what happens in the other functions, right? So you pick this atom and put in the underground warehouse, right? So you need to decompose this, as I told you before, to fit the mark. So you pick this atom, decompose in pieces to fit the marks that you see here, as before, right? So you have infinite many of these yellow things there. I'm just studying what happens with just one of them, this yellow one. So when I apply the Perron-Frobenius operator, this map is expanding. So you go to a higher level, right? You go to a higher level because the base expands and you apply the Perron-Frobenius operator. So you get this blue thing like that. But this guy is not an atom. It doesn't fit the marks. So you need to decompose again in blocks and put in the appropriate positions. So you just decompose to fit the marks in the floors on each level, okay? So that is the action of the transfer operator in the tower, in the warehouse, underground warehouse. Good. So, so how you study the transfer operator? So this action has why you have contraction, you have quasi-compactness of the transfer operator in this setting? Because of the following. Pick an atom in some level, right? So you have this atom here, and pick in a higher level. So the atoms in higher levels are smaller. They are not so tall as this one, right? And if you compare the area of these two, right, the integral of these functions, you see that if the measure of Q is bigger than the measure of P, then this area is smaller than this area. So the area of the blue one is smaller than the area of the yellow one. Okay, so those are two atoms, but with the same different areas. This one has bigger area. So what you see, let's see what happens in the tower. So suppose that you have a very regular, it's just the idea, right? Suppose you take an atom and apply the Baron-Frobenius operator. So because this atom is very small, you can assume that the potential is constant. So A goes to a picture like this. But because this is the Baron-Frobenius, the area of these two regions are the same. The Baron-Frobenius operator preserves areas. But an atom at this scale is bigger than this. This area is bigger. So that means that the image of this atom is just a fraction of the atom, of the original atom, right? So this is a fraction of atom. So you have contraction, at least for small atoms. For small atoms, you have these contractions that you see here. Okay, so that's basically what you do. You start with the function that I might call psi. You make a representation in this space. You decompose as blocks. You need to find a good representation. Cannot be like as I told you, there are many possible representations. So you pick a representation that's good, right? It's like the optimal representation. Maybe it's not perfect, but it's very good to be very close to be optimal. So that means that when you go for this representation, the perfect representation, and this not so good, you lose a factor that's bigger than 1 in this representation. So this is the bad stuff. The green stuff is the bad stuff. So the next step is dynamical slicing. This is also bad because you are going to change this representation that's quite good by something to fit the properties of your dynamical system. So when you do this, you lose some control and you need to multiply this. So the new representation of the function that you get is worse than before. You need to multiply these two bad factors that appears. So the action of the tower is the only step where you can have actually contraction. So in this step, you can have contraction. So this is the good stuff. The blue one is the good stuff. And you have some factor, multiplicative factor smaller than 1. So you get a representation in the end that is not so good, but this factor maybe kills these ones and you have something smaller than 1. And finally, you put together all the things to get the Baron-Frobenius operator applied to the original function. And this is also, you can lose something in this. So you have also a factor that is putting together things could be bad. So in the end, the norm of the new of the Baron-Frobenius operator psi is controlled by the norm of psi multiplied by these numbers, this product here, right? So this is basically how you prove that the Baron-Frobenius operator is a bounded operator in these spaces. But what happens is that to prove quasi-compactness, there is an additional factor that is the following. I'm finishing. That's the following. If you pick a big atom, when you do dynamical slicing, this atom can cross many domains, many branches. That means that you need to cut many times. So when you do the dynamical slicing, this factor can be very big. So imagine like you have an interval map with 10 branches. If you pick an atom that is very big, the support is going to intersect like 5 branches, right? So this, because you need to do more slicing, this number is going to be very big. But if you pick an atom that is very small, has small support, then, for instance, for interval map, is going to intersect just at most two intervals, two branches. So this number is bigger than 1, but is much smaller than in the other case. So the point here is that there are just a finite number of atoms that has big support. Most of the atoms has a small support. So you can decompose the psi in the contribution of the large atoms and the small atoms. For the large atoms, this number may be very big, and this could be very big, but doesn't matter. That means that this is a bounded operator. And what is nice is that because you have a finite number of atoms, lives in a finite dimensional space. So the image lives in a finite dimensional space. So this operator that associates psi with this number is a bounded operator of finite rank. This does not influence the essential spectral radius. The other part is more interesting, the small atoms. Now, you may have infinite many atoms, probably infinite many atoms there. But because the support of the atoms are small, the dynamical slice is not so bad, and maybe this is smaller than 1. And if this is smaller than 1, you have a contraction here. So this is a bounded operator, that's a contraction. So you wrote down the action of the Frobenius operator as a sum of two operators, a finite rank operator and a contraction. And this proves that L is a quasi-compact operator, okay? And I don't have more time, but in this case, for instance, you can easily do all the calculations because this is a Markovian one. So that's a toy model if you prefer. So in this case, you can pick the dyadic partition, and the dyadic partition is the Markov partition of this map. So if you pick, and you can do all the calculations in one page. If you pick an atom like this, it goes to atom to twice the support, and you have this contractive factor, except for the atom that is the full interval. So this is the only one where you need to slice twice, slice once, and you have the quasi-compactness in this case. So in this case, 2 pages, you can prove everything. Okay, so I think my time have an end, so thank you very much for your attention.
Thank you, Daniel. It was a nice talk. I would like to know if are there some questions, comment?
I have a question. Actually, first, a point of clarification, Daniel. So you, when you choose this sigma filtration of sigma algebras or martingale structure, independent of the dynamics at first, it just has to do with maybe the geometry of the phase space, and then you use the dynamics to construct a transfer operator to fit it to this filtration. Right?
You use the dynamics to.
This is what the dynamical slicing is to force it to conform to the previously chosen sigma algebra filtration.
Exactly like that. So if you pick an atom like this, for instance, it fits the mark. This is the composition in this space, but doesn't fit the tower, right? So you need to do this dynamic slice to fit the underground warehouse. So this is another representation in the same space, but is not so cost effective as the previous one, right? But you need to do that to apply the performance operator.
Okay, and well, my question is there an analog of this of the transfer operator in this setting to some operator in Fourier analysis? To me, this looks like a kind of Fourier multiplier on some wash base.
Well, if you see that I don't know. So this is like, so Frobenius operator is like a combination of pointwise multipliers, right? You pick a function and multiply by some potential, but it's not exactly like that because you need to compose it with the inverse branches. So it's like a weighted composition operator, right? I think that's the terminology people use in analysis, right? And yeah, I think there is something similar, but I really don't find anything in the literature so like this, right? So you can apply this, for instance, for Kopman operators or composition operators in many settings. So if you're not interested in to prove that the map is quasi-compact, you just wanted to prove that it's continuous, right? If I just wanted to prove that the operator is continuous, preserves the below space is continuous there. This also gives you some things about to study composition operators in this setting, right? And multipliers. You pick the function, multiply by some potential. You wanted to prove that this is a bounded operator in the Bezold space, right? So there are many results about this, and this somehow generalize some of these results. I don't know if I answer your question.
Well, I have to think better.
Okay.
Thanks.
Okay, so more questions? Are there more questions, comments?
Yeah, well, may I? Well,
Yes.
first of
Yes,
all,
Pedro.
thank you very much for this beautiful talk.
I'm sorry, Pedro, for interrupting you, but there is a comment of Viviane saying that about the question of Silvius, that's saying that you can also prove quasi-compactness in Fourier space. Okay.
You mean to take Fourier transforms and apply? That's what you mean? I think Viviane is not, yes.
Yes, she means
so the problem is that I suppose that in one-dimensional setting you can do that, but imagine a homogeneous space or a fractal. So in this case, you don't have Fourier series, you don't have Fourier transforms and things like that. So I'm sure that you could use harmonic analysis, but not Fourier transforms, right? Yeah.
Well, she said not necessarily for exactly this space. Well, she wrote a book on that.
Yes, I know.
But she had a smile in the end, I should say.
Yeah. Yeah.
Can I ask something? Can I comment something?
Sure.
Yes.
You see, you are considering atomic measures. Now, for atomic measures, if you put the weights as 1/2⁻⁴, the range of the measure is convex. And in a unique way, except for those terminating and recurring things. But there are many other sequences for which the range is convex. Its range is an interval, and they are called interval filling sequences. So when you have interval filling sequences, what will be the effect on your corresponding operators? Your atomic measures, the weights are such that they are interval filling sequences. And that means the range of the corresponding atomic measure is convex.
Yeah.
Because if you integrate over bounded measurable functions, then that set is convex, but we do not have to integrate. Only pure strategies are enough.
So I'm not sure.
And like, 1/3⁻n is not interval filling, but 1/q⁻n for q between 1 and 2, the sequence is interval filling.
I think I'm
and the only difference from 1/2⁻n is that it happens ever so often. The same point can be reached via different combinations also. And this was given by Kakeya a long time ago. And my student Laltan Pua and I have a paper in General Convex Analysis 2008, where we consider atomic measures coming from interval filling sequences.
So I'm going to be very happy if you send me the preprint. I'm going to be glad to.
Okay.
Thank you very much.
So now we should pass the word for Pedro. Pedro, please.
Yes.
Sorry for the interruption.
Yeah, no problem. I just want to ask what may look a silly question, but actually it's not really a question. I wanted to have to see if I get the right intuition for these Bezold spaces that you are considering. So I imagine these are spaces that are much more general than other continuous functions. I imagine they can have discontinuities. But is it true that when you, so this is an intuition that I want to see if it corresponds to the right picture. Would it be true that when you take one of these Bezoff functions and when you look at one very small element of the partition, then in some rough way it looks older? Of course, it may have discontinuities at lower scales.
You can
but
see these functions as combinations, linear combination of piecewise holder functions, but it's a infinite many. So you can it's like in Young towers, for instance, you consider piecewise holder functions, right? So it's pretty much the same. So I think exactly how you're thinking about it. I'm thinking like piecewise holder functions, but you need a complete space, you need a Banach space. The discontinuities can be in any place. So you need a function that contains all this weird stuff, these piecewise holder functions, and that's Bezoff spaces are the nicest spaces to work with. So I think that is the intuition. You may, is wrong, but you can think Bezoff spaces within this S was piecewise S holder functions. It's not the same, but, because you can have singularities. For instance, you pick a log of X belongs to this space, for instance, right? So you can have unbounded functions in this Bezoff space.
Okay, thanks. Thanks a lot.
Yeah.
More questions? Some comments?
Can I ask something?
Yes.
So I was wondering how much do you use actually hyperbolicity? So can you do something similar if you work, for example, with an Ossoff system? So there was a work by Liverani and Mark Demers, which were proven something, well, they were proven that that Lazotte-Yorke inequalities, for example, for an Ossoff system. So I was wondering if you can generalize this to that case.
So not these spaces in particular. I think they, when you work with an Ossoff diffuse, you need to have some anisotropic things. So we have different behaviors in different directions, right? But I think you can use atomic decomposition. So the method of atomic decomposition, I'm very optimistic that you can use in this setting. So you can define a space that is anisotropic using atomic decomposition and prove quasi-compactness in this setting. I didn't try. I confess I didn't try, but I think it is possible. Somehow it's like standard pairs, right? In some things, you have these laminations, and in each one of the stable lamination, I don't remember, you have a Bezoff function, right? It would be something like this, but you need some regularity in the transversal direction. So you can use these blocks to build functions. So the atomic decomposition is a very powerful method, actually.
And would so in your case, singularity is a problem? So for example, if you have, I don't know, hyperbolic map, which, well, if you have a map with singularities, would they cause any troubles?
Okay, so so depends on this. So Lorentz maps has singularities. It's not this kind of singularities that you're looking for. I mean, like,
I'm sorry. Can you just show me? Can you show Lorentz map again, maybe?
Lorentz maps. So it's a spanning map, right? It's not a critical point, but it's a singularity. So.
Oh, okay. I see. No, this is not it.
Yeah, this one, right?
Yeah.
So you have x to the power L, where L is between 0 and 1. So in this case, you can apply these methods. This is kind of a special case. You need to work harder in this case to apply the theorem.
Yeah, you always have to work harder when you have singularities.
Yes, yes.
Yeah. Do you think you can share?
Yes.
Do you think you can share the slides?
You can get the slides. Yes.
Yeah.
Yeah, I can send you. Yes.
Okay, great.
You will
Thank you.
be able to see the talk in the homepage Monday. Okay.
Yeah.
Maybe you will repeat the homepage in the chat, Lorenzo, so she can. Since you are in this slide, Danielle, I would like to just, since you didn't show the main result, and I imagine why, you showed some examples from the bestiary, all very nice. But are these the results, like these, for instance, this result that you obtain for the density, kind of the support of the density has
yes.
These are all the, it's not for the examples, it's your main result has also this implication.
Yeah. So the point is that if the potential positive in a strong sense, for instance, if you pick a potential that is holder and positive, you can make these compositions in the Bezold space, and all the blocks are positive. All the blocks are positive. So that means that using this information, you can prove that the density is going to be at the Bezold decomposition in such a way that all the blocks are positive. So it's a linear combination of piecewise constant functions. So it follows immediately that this set is a set that is a countable union of these elements of the grid, right? So it doesn't really matter. We just need this assumption that the potential can be right and has a positive combination of positive blocks. If you can do that, like holder, positive holder potential, or positive boundary variation potential, then you piecewise C1 plus alpha maps in the RN, you can apply this. So this, I think, you cannot prove using Fourier analysis, even in the interval, even in RN.
Okay.
Because it's difficult to talk about positivity in this setting. So.
All right, thank you. So more questions? If not, before we thank Danielle again, I would like to recall you about the invitation for next Tuesday. We have a conference day. It's New Trends in Lyapunov Exponents. This conference was supposed to happen in Lisbon next week. Unfortunately, it's being postponed for next year. Maybe Pedro wants to add. I have put the page, Pedro, in the beginning, but I think you're not there. If you want to add something.
No, it's.
So, okay. I will add again the web page in chat, so you can get the Zoom link there. I hope see you all there. But now let us thank Danielle again for the very nice talk. Thank you, Danielle.